Testing, testing. Can you hear me? Good. Welcome to our talk. If it's live with actors, we'll be talking about akka.net mostly, and a project is an experience-based report, so it's a project that's been running for, I think, just over a year, which will show you some experiences during this project. But first, let's introduce yourself. Who are you, Vagif?
Good morning. My name is Vagif. I'm originally from Russia, as you can see from these Cyrillic letters. But I've been living and working in Norway for quite many years, and last few years working with some interesting projects at NRK. It's a Norwegian Broadcasting Corporation. I'm consultant working for a company Miles, and in this last project, I've been working together with Erlend.
Yes. And this is me. I'm also mainly background in C#, but recently, well, the last few years, I've been doing F# a lot. And this is, as you can see on the text here, or you can't really see, but it's an Emmy award, which I haven't won, but I could take the picture at least. It's actually for a children's show that we produced at NRK. And this is NRK, as Vagif said, it's sort of the BBC equivalent in Norway. So we're a public broadcaster owned by the state or the government, and we are funded by the people. And this is a picture from our first live TV broadcast. In the middle, the guy in the shot, I think, it's the king. It's King Olav. The guy on the far right is the prime minister. He's called Gerhardsen. And the guy next to the prime minister is the third guy.
And it was before fake news, so the whole thing is real.
Yeah, but we haven't found out who the third guy was. He's like the third guy on the Apollo 11 mission, along with Buzz Aldrin and the men on the moon. So, a short timeline, like we said, the first TV broadcast was in 1960. But we've been around doing radio since 1925, 8 years as a private company, and then it was founded in 1933. And today we have over 1 million programs in our database, which is cool. But due to rights, mostly, around 120,000-130,000 are available at any given time, and that's combined TV and radio. And our product looks like this, at least on an iPad. Of course, we have multiple platforms, Apple TVs and so on. As you can see, it's a modern web player, and our main competitors are Netflix in the Norwegian market, and YouTube and so on, all the giants from America.
And this is our system.
This is our system. As you can see, we've been very creative during this, trying to create this talk. We've been drawing a lot in OneNote, and our project is the square box in the middle here. DE stands for Distribution Engine, and that is our project. We take some programs from internal storage, and we distribute them to the cloud. That's been Akamai. And on the far back end, you can see that a program is typically made up of 5 files, which are encoded in different qualities, ranging from 720p, I think it's the highest one, to a very low quality 180p. So that is the project.
A lot of files, shared state, parallel processing.
Parallel uploads, yeah. We try to distribute things as fast as possible, and that's where parallelism comes into play.
And that brings us to the point why we needed to do something with it, because as Erlend said, we actually started doing it from 2012, so actually we have a working, stable system. But as you saw, with a lot of files processing parallel, then it's a lot of manual thread management, it's a lot of locking state management, so the old system was really hard to maintain because it was not many domain-related things. It was mostly thread and state management. So then we started looking at different programming models which would simplify our work, so we could get rid of all this. And then we found that actor model, and in particular actor.net, since we are in .NET, was a good fit. And in the rest of this talk, we're going to talk primarily about main lessons, especially main lessons for us as developers with object-oriented background? Who considers himself or herself developer with object-oriented background? Yeah, I guess majority. So are we.
Vast majority, yeah. Which leads us to, again, a simple drawing of our existing system. Vagif mentioned it. This is a system written in C#. Fairly well written 4 years ago, or 5 years ago now. But as we've mentioned, we had quite a few issues around threading. There was spinning up of multiple threads, trying to do multiple uploads. There was a big repository of tasks, so I had to lock the repository and make sure you checked in some tasks and checked them out. And there was also, the green one is the database. A lot of the state was actually kept in the database with various amounts of flags. So it's a typical software development story. If you want a new feature, you add a flag in a database, which leads you into trouble. So you wanted to get away from these horrified monkeys.
That was the design goals, to get rid of this.
Where did you find this picture? Yeah, so we wanted to get rid of the actual manual handling of threads. I consider it a bit like memory management. You want to get away from it as much as possible, at least in general programming models. And we wanted to enforce more of a strict mutability, and we wanted to use F# basically, a more functional approach. Since this is a very back-end driven data transformation type of project, the C# implementation was trying to do it functionally, but a functional language is better at doing it functionally. So we ended up with these two choices, akka.net and F#. And I think F# was the obvious choice for us, as we've recently become quite big fans, both of us, in different projects, so it's become more or less the default language in our team, so that was easy. Akka.net was maybe not that of an obvious choice, but we read some stuff about the actor model and I thought it could help us isolate some state around these uploads, around these programs, so that we maybe can model each upload as an actor.
And by the way, who has no experience with F#? Please don't leave the room yet, because our main lessons are about programming model. F# just implementation language.
Yeah. And there will be music at the end, so you have to stick around for this. It will be worth it. So,
how to introduce actor model in just a few minutes. The best, probably you should find the proper picture. And of course, when we started Googling for actor model, this is the first picture, not diagram, we found. And actually, in some presentations, actor model is illustrated with a picture of Fiber, which was completely unacceptable for me because I have in our family Fiber. This is my Fiber, so we couldn't use that picture. Fiber instead will focus on the actual description in a few slides how actors and actor model work.
Yeah, this is a diagram showing the actor, or one actor.
This is an actor.
Several actors, actually. An actor is simply a message loop. On the far left, you can see you interface with an actor by sending it a message. That message gets put on a queue, which we usually refer to as a mailbox. And it's important to note that one actor has its own mailbox, so these queues are not shared among actors. Every actor has its own mailbox. And when the message gets put on the queue, the actor starts reading the message one at a time. It's also very important to remember. So it has to finish the message before it can start anything else.
And as you can see, that one message at a time, and also just messages. Can an actor have a state which is visible for others?
No, it controls its own state, so it's not like an object. You can't access the property and so on. You have to send it a message. If you want to ask it something, then you ask it by sending a message. Similarly, when we talk about actors, we also refer to an actor system or an actor hierarchy. This is a very simple illustration. A system is a namespace, I think reserved for logging and some operational things. And the space you use mostly is the user space,
where we create our actors.
So you create a hierarchy, parent and child, and supervision, and someone will come into that later, because the hierarchy is quite important. On this slide, we try to illustrate that just because it's a hierarchy doesn't mean that you only can pass message to your children or your parents. You can actually pass them along any way you want, actually. You can obtain a reference from the lowest level to the top level, actually. Whether that makes sense is up to you. You still have to be intelligent when writing these message flows, but there's no inherent thing stopping you from passing messages all through the hierarchy. But actors are quite different from objects. In what way, Vagif?
Yeah, for us, it was a big change of perception how actors work compared to objects. Objects, they don't have a really embedded notion of threads when they doing their things. So objects are bags of properties. You can give them human-readable names. You can call them Pete and Mary, but they can be easily bullied. So anyone who has a thread can access public methods or public properties and start changing objects. So, and then we say that object is not thread safe if you can't really do changes to it through multiple threads. And that's, of course, a big problem. Actors, they don't own threads either continuously all the time. But what's different is that an actor, when an actor gets a message, it borrows a thread. And whatever he does to its state, if needed, it's just its own sole responsibility. So if actor changes the state, it's only that actor that changes the state. That makes it much easier to debug actors in case you have some problems with that. So no shared state, no threading. That makes it very, very different and very applicable to this enterprise system with a lot of parallel processing.
Yeah, and this is a simple, this is actually a C# example, which we wanted to show. As we mentioned earlier, we'll mostly be showing examples in F#, but let's look at the very simple implementation in C#. It's a class, it inherits from receive actor, it has a constructor, and it has a receive method. That's quite important. So receive is like, well, in JavaScript, like an on-receive message. So when you receive the message of type user message, then you do something. There's a lambda expression here, just doing very simple logging in this example. And similarly, an example is in F# is a bit more alien to him, perhaps. There's some stuff going on here. There's bangs and stuff, and there's loops, and yeah.
But in essence, it's the same thing. We're getting a message, and we...
The main lesson is the same thing. It's a continuous loop, asynchronous loop, receiving a message from the mailbox receive message. It prints printfn, prints the message, and then returns the loop and tries to receive another message. Let's look at a bit more interesting example.
Now, that's something more interesting from operational point of view, because this is an actor which implements a simple state machine, FSM. So it has two states, disconnected and connected, and each state is managed by so-called function, because in F# everything, of course, is function. You try to use only functions for that. So this is a function which takes messages, and then it reacts on message connect, and then it creates connection. And then it goes to another state, which is also implemented using another function, connected. In connected state, we only respond to disconnect messages. Otherwise, we do respond, but we don't do anything. We stay connected. So you see, it's very declarative. We have states presented as function, and also it's quite declarative, like what messages we respond in every state. And of course, we need to specify what is initial state of this actor, is disconnected state. So these constructions we use quite a lot in our project, and it's really easy to read, it's really easy to maintain.
Yeah, that takes us to just remind you of the agenda. We'll finish with our introduction now, and we'll move on to the main lessons. And by starting with tell, don't ask.
Yeah, that's the first main lesson, probably far the most important lesson that we learned. Because when we started with actor model, we saw that actor has two methods, both looked very convenient, tell and ask. You use tell, we just send message to another actor. And you use ask when you send message to another actor, and you don't do anything else until you get a response. And then we thought that's the best of two worlds. Let's use them both. Of course, we try to use mostly tell, but in case we need answer now, we just wait. First of all, that breaks reactive software principle, because when an actor is waiting for a response, it's actually consuming CPU. It's consuming a thread. But then, what if response never comes? And this is not fine, and this is a frightening picture. It shows actually a number of hours which we spend debugging such actors waiting for a response that would never come. And I probably should have specifically bad conscience because I'm external consultant using these hours. But there is more than that. The performance of ask operation is just horrible. And let's have a brief look why. So we use this machine, small machine with Intel i5 to run some tests. And just for the reference, the fastest thing you can do, of course, is direct method invocation. And then you can call a method about 300 million times a second on this machine. And all other operations which we tried, they're so much slower. So we decided to remove this from other slides. Otherwise, we wouldn't really see the real thing. So when two actors talk to each other, just sending a message to another actor is also pretty damn fast. It's 3 million, about 4 million on this machine messages you can send from actor A to actor B, which is approximately 10 times faster as using async await if you use TPL library. But if you use ask, performance drops dramatically. You have only about 150,000 messages. So it's really horrible performance. If you want a long answer to that, you should read the blog post written by one of Akka.NET contributor, Bartosz Szepetkovsky. But in brief, the ask implementation internally is actually quite complex, because everything is message in actor model. So let's say an actor A sends a message to actor B, and then it needs to get a message back immediately before processing anything else. So there is a message coming its way. If message is received in the regular mailbox, what if there are other pending messages that needs to be processed? But it can't. It needs to respond to get message the response first. So we either need to rewrite implementation of mailbox, which is sadly not sequential, or we need to do something smart. And both creators of Akka Scala and Akka.NET, they did alternative resolution to that. So actually they create a third actor with the sole responsibility for waiting for this response and delivering it using kind of priority delivery to the actor A. So you see, 3 actors are involved just to get a response back, which of course makes it complex and makes it slow. So what if you really need a response from actor and you can't do anything else until you get a response? What works very well actually is implement so-called integration pattern, where you add simple finite state machine to your actor, which actually brings it into a waiting state. So you can wait for a response staying reactive. Let's see how it can be implemented. First, the original implementation. We have an actor that receives a message, and if it receives a message process item, it needs to fetch some more details. And here it's the old implementation. It's waiting for response. This is an F# ask method. Get item details. We are waiting. So we are in hands of this other actor, and we still consuming CPU. How can we rewrite it? Let's introduce now simple FSM. We can be in idle state, and if we get the message process item, we just send the message straight get item details, and we enter new state, awaiting details. And we actually go to sleep until we receive the response. In this new state, if we can't process incoming message, then we stash it. That's a function of Akka. So you can stash messages in some intermediate queue until you can do something with them, staying reactive. Once you get this new message, you get these details and send them to interested party, and you unstash messages that have been waiting. So this keeps your actor very scalable and reactive, and no longer you have this synchronous loop waiting for responses. And if you look at performance of this, it's actually not that bad. Of course, it's slower than tell, direct single message between two actors, but it's actually several times faster than using TPL. Yeah, this is async task. Yeah, TPL. So this is our preferred way of implementing bidirectional communication now in our system. Of course, we still use ask in some cases, but this is mostly some system calls, some calls to actor system, like asking for reference for an actor, querying persistent actor we'll be talking about later. So mostly our system now implementing using unidirectional messages. And that brings us to the next important lesson, probably the second of its importance, actor supervision.
Yeah. Let's look at actor supervision, or error handling, as it is. Actor or error handling in akka is quite a bit different than in C#. We'll look at that. We try to get away from handling actors in a very small local scope, and we try to do supervision on top of that and say, fail fast and easily down here, but take care of it up here. So we actually have another example in C#. That's true. Didn't remember that. But this is an example trying to connect to a database, I think. And what do you do in C#? Well, you slap the try-catch around the command you want to execute, of course. As probably a lot of you have done multiple times. In this case, we are not doing very much. We are just wrapping it in some sort of custom exception, which is very nice and enterprisey, I think.
But it's not good enough.
It is not good enough. We can do it even more enterprisey. We can catch multiple exceptions. There's probably, I can't remember how many exceptions the connection is able to throw, but I guess it's approaching double digits, and how many different argument exceptions and all these kinds of different exceptions. But what's important here, and you can read in the code or in the comments, is what do you actually do inside these catches? Do you just log the error and rethrow it and hope that some other being on top catches it? What do you do if the connection is shared among 100 different methods? How do they recover when the connection is suddenly dropped? How about the threads? How are they able to stay on top of this? It becomes very difficult. And we'll just have to reference this other article or paper, which is very good and explains it in quite a good detail. The very sticky situations you can get into with the control flow when you try to handle these errors locally, particularly in more modern parallel paradigms. So let's try to explain how we did it in akka.net. And this is a very simple example of our interface, which deals with reading messages from a queue. Not the internal actor queue, but external queue like RabbitMQ. We use RabbitMQ a lot. So this is a command. As you can see, to connect to the queue, you have to connect, of course. And once you're connected, then you have to subscribe to the actual queue name, or give an actor that's supposed to receive the message after you've read it off the queue. And the implementation looks a bit like this. As before, it's a mutually recursive function and an FSM that deals with what transitions between all these states. But errors occur always, not just in the C# code. It will probably, the database can go down in, there's no magic in functional programming that you won't lose the database. And you have to handle that error. And in akka, it is dealt through a supervisor strategy. So a supervisor is the parent of the child. So as you remembered earlier, we had an actor hierarchy, and the parent also is, when the parent creates the child, it's also sort of responsible for that child, just as in real life. And what happens when an exception occurs in the child then depends on the strategy. And the strategy can be applied just to the failing child. So if the child falls down and breaks its leg, you take the child to the hospital, or maybe you're a doctor yourself and you fix the leg. I'm not sure. I usually take mine to the hospital. You could do the same action for all your children. So if one falls down, you take them all to the hospital. I guess that might make sense.
Yeah, being the only child in my family, I find this not fair, this strategy.
It's nice to go to the hospital. But so you can choose, just handle the one message, or maybe it's just that child is part of, say, 100 workers doing the same job, and all need to restart them, for instance. Because what you can do, there are 4 types of things you can do. You can just restart the actor, just say, oh, exceptions, that's bad, try again.
And that's default.
That's the
If you don't specify anything else, this is what will happen.
Yeah. Or you can resume. So we have the mailbox, and one message fails, but that doesn't really matter. Maybe it's a video stream, so if you lose one frame, that doesn't really matter. So you can just keep on processing. You could actually just stop the actor, give up, or you could really give up and just escalate the whole adder to
Grandparent, yeah.
To grandparents, or
who always know better.
Government, or supreme being of some kind. And this is a simple example again. The strategy, as you can see, is 1 for 1, so this is just the one actor. And here we can also be quite enterprisey and catch all these different exceptions and do different jobs depending on the exception.
But what is important that this strategy definition, it replaces all those scattered around try-catches everywhere. So you define this in one place, typically on the parent level. In case parent encounters these types of problems, what needs to be done to actor? Stop it, resume it, and so on. So no more this logic inside the catch.
That is true. And let's be really explicit and just show you what actually happens. The exception occurs, the exception gets thrown, so it suspends the runtime, the actor is suspended. The supervisor gets notified, the supervisor then gets rid of the actor. But what's important here is that the supervisor gets the mailbox. So say there was 1,000 messages pending on this actor, and one of them failed. The parent gets the other 99, or the whole mailbox actually, and can re-instantiate the actor and give it all its messages, so you can just try again. And what we realized with our implementation was it was quite, I think it was
it was wrong implementation.
Yeah, wrong implementation basically. It's very much modeled after this C# API. What happened here is that when you restart the actor, it gets the mailbox, yes, but it doesn't get the messages replayed that made it go into a certain state. So in our case, when we first started up an actor, you had to actually send it a message to connect and then a message to subscribe. And when it gets restarted, it gets into a blank state. It receives the messages or the mailbox, but it's not actually in a state to be able to process some messages. So we had to inject those, doing similarly to dependency injection. You have to actually have to send in functions or messages that makes the actor able to start working right away. So we could get rid of a lot of the API, making it a bit less explicit. And we ended up with this. Now it's just a one function. And on the top, you can see that we send in the constructor, or it's called props in Akka.NET, properties. We send in the actual details of the queue, so the address of the queue, the name of the queue you should subscribe to, and also the subscriber, the one that is going to do the next step in the pipeline.
And if you remember the first implementation, had 3 states: disconnected, connected, subscribed. But it doesn't make sense to create an actor disconnected. It should be as operational as possible. So just one state, and we try to send anything that we can to make actor up and running in case it will be restarted.
Yes. Which takes us to
the next lesson, which actually was not essential reason for us to choose actor model. we read about so-called persistent actors, but we thought it will be a nice addition to regular database, because in every backend project you need to have regular database. And after a year of development, we can be proud to say that that was a year without creating tables, without writing auto table. Everything, all our persistent needs solved by so-called persistent actors, which are implemented using so-called event sourcing principles. So an actor receives commands or messages, and they all can be treated as events. And if you need to play them back, if you take care of them, you can do that. So the persistent actor is the one who actually stores all these events in so-called event journal. So these are all events that happen to this actor. For performance reasons, for optimization, you can also have snapshot store. It's typically another table in your backend where you can store some states periodically. So if you want to play it back, you will play back quite fast. So this is an example of persistent state that we take care of. We deal with file distribution. So in our system, we need to take care of locator, where in the cloud file is located, storage provider, its CDN path, and so on.
Is this production code, isn't it?
Yeah, it's actually, it is from production code, and these are 4 commands that we send to our persistent actor. We can assign locator, we can remove locators. That's the only case where we use ask, actually, query locators. I said earlier that we still use ask for querying persistent actors, and we take snapshot for efficiency reason. And there is a wide choice of backends for Akka.NET. We're using Microsoft SQL Server just for reason of maintainability and operation, because at NRK there's a lot of competency and good operations around Microsoft SQL Server. You can choose anything that you would like to. Of course, MongoDB or even Event Store. It's not listed here because it's not officially released, but you can also use that. And just for curiosity, that this is how event journal table SQL Server looks. What's important that you must have global unique persistent ID, which is up to you to assign. It has sequence number, so it will be played back using this sequence number. And of course, the event content is here. It's payload. But again, this is something we just copied from GitHub and applied to the database. We didn't do it ourselves. And being backend developer for quite a lot of years, I must say that that was not my most creative time I've been doing in my life, creating and altering tables, and just focusing on domain tasks and outsourcing to persistent actors was quite a relief. And then next question about a lesson about configuring actors.
It's about scalability. So. Which leads us back to this actor hierarchy. And one of the main advantages, I think, of Akka implementation is that it's very easy to create a lot of parallel tasks or sort of worker threads. They're not threads, they are actors, but they are. If you have a task that's supposed to break down something, maybe something you can easily split them up to 10 jobs or maybe 100 jobs, 1,000 jobs, it's very easy to create that parallelism in Akka.NET. And it's done through routing, which is similar to supervision, is defined on the parent level. You define how the messages should be distributed among your children. And you can do that in several ways. There's round robin, you all know this. It's just evenly distributing them. You could do the smallest mailbox and say the one that doesn't have much to do, he should get the message. This doesn't take into account stashed messages, so you might run into some trouble there. But the one that we have been using a lot is consistent hashing, where you give the actual router a function saying, based on this hash, you should route the message to this. And we use this for the separate programs. As I mentioned, we have 1 million programs or 120,000 active programs. And each of those programs are a separate actor based on the hash, which is based on, I think it's the unique ID and some other characteristic, yeah.
Yeah.
So this example shows you the very basic creation of an actor. So this is just creating one actor. The Akamai upload actor is the actual function, and it has some properties. Yeah. And this one shows a bit more code, but this is actually all you need to write to create. There's a limit here somewhere. I can't remember.
Yeah, or you can put everything in configuration. It works as well.
Yeah, well, it's limited by some configuration, but I think we have a lot, or at least 100,000 different actors created on the hash function, which is the Akamai uploader get hash base. So that returns something which uniquely identifies your actor, and then every other message that gets passed into this parent actor then gets routed to the correct child.
That prevents same files be processed by parallel actors simultaneously.
Mm.
And probably what's important, if you go back one slide, that this actor doesn't know about it. It's configured, so now it's running in hundreds of instances. Yeah. The code is still the same.
Yeah, so the actual actor implementation, you don't have to rewrite that and say new up 100 or something. You define it on the top, and the actual function is still the exact same, more or less. Yeah, which takes us to the much promised musical break.
Yeah, there's been quite a lot of content, and so we thought that it would be time before we go to the final part of our presentation to let you easily memorize the things by presenting a song about it. And this song might, of course, must be written by English musician, in this case Elton John, and we will be covering several topics in the song. Of course, you already know that actors...
You say we, but this is more of your...
yeah, it will be helping with the slide.
Your domain.
Yeah.
This is where I become a sort of embarrassed and try to...
Erlend refused, but you can sing along. So actor process one message at a time, we all know, and actor instance created using set of props, and the reference to actor is called actor ref. And if a router creates multiple instances of actor, they get names $A, $B, and $C, and our hero will get name $B.
Beautiful names.
Yeah. And then, of course, you have supervision strategy, and the most crucial one, or cruel one, is all for one, where all actors are restarted. And of course, you should try to use tell and not ask. So with that, we will see if we can...
see if this keyboard works.
Yeah, actually, it looks like... So now you're helping with text,
yes,
and everybody can sing along.
Or not.
Goodbye, $B, though I never knew you at all. They chosen to restart you, and your instance got your name. But when you were alive, you played your role according to your props, and every single message knew that for you she's only one. And it seemed to me you lived your life like a good reactive code, only using CPU cycles when the message came. And I would have liked to have known you, but supervisors found your instance burned out long ago. Your actor ref will last. Most of the time, and when you were awakened, they let you tell but never ask. Even when you died, it was another sibling's fail, but supervision strategy was clear and brutal, all for one. And it seems to be you lived your life like a good reactive code, only using C when the message came. And I would have liked to have known you, but supervisors found your instance burned out long ago. Your actor ref will last. Your instance burned out long ago. Your actor ref will last.
Beautiful.
Thank you. Thank you. Are you ready for with more technical stuff now? Well, that was also technical. Testing.
Testing.
How we tested actors?
Oh, how can we go back to testing now?
Yeah, there is Akka test kit.
This Akka test kit, yeah. I think one of the main lessons we learned that, of course, well, and recently there's been a big debate on testing and Uncle Bob and so on, but I think we started a bit late on doing our testing, and you shouldn't really underestimate testing, even in a functional language and even in an actor model and whatever fancy framework you're doing, you should probably do some testing and verify that the stuff works as you expect. And Akka test kit helps you do that. It fits well with the functional paradigm, so it's an input and an output, and in an actor system's case, that is a message in and the message out. So you can actually send it a message and then verify that it sends a message you expect further along.
Yeah, so that's basically the essence of testing actors. You have incoming messages, and then you expect certain output messages. And then if they're okay in relationship with incoming messages, then your actor is good. But we are also using so-called FS check. Who knows quick check or FS check? Yeah, quite a few.
Yeah. So FS check is very heavily influenced by quick check, sort of a port from quick check. And what this helps us do is randomize the input of our messages. So in this instance, you can see that we on the very top line on the far right, you can see that we get a message that is of type upload job. Then on the bottom here, you see that we expect some certain messages or sequential messages being handled.
So these are message types or message names, and this is order. So if there will be a wrong message, a wrong order, then we will have an error. But look that we didn't specify the initial data. They will be automatically sampled by FS check.
And in this case, it's just it tries to create 10 different. So it's 10 different variations of the upload job. So it looks at the type, looks whether it's a string and so on, and tries to infer the data types, of course, and then it tries to manipulate those data types and basically tries to break your system. And that helps us a lot, I think, with actually static typing. Correct?
Yeah. Who follows this recent Twitter war started by Uncle Bob, who claimed that static languages sometimes are too rigid, too strong about things, and then you shouldn't really replace your test with it. You should sort of rely more on your test. Who has been following this? Yeah, Uncle Bob, of course, he has a lot of valid things to say, but we must say on our side that actually we're using quite extensively the static type system, because when we started with this upload job, we used types like strings, ints, and then our sample generator just generated some rubbish strings for us. Of course, you have a file name which consists of commas or null strings, and then this is a noise which is not worth testing. Then we slowly started turning into strong types. So now we have type URL, file name, alphanumeric, and so on. Once it was done and we have proper generators for everything, then we get actually data that has a lot of sense. And so we can get here in this test 10 samples, but usually by default, like hundreds of samples you get for free, basically, from test generators. And it's all dependent on good, strong types behind.
I think we also had some file paths, so like a C : something path, and then the FS check would just create a string with just numbers, which doesn't of course, it's a valid test if you want to make your system really handle everything in the known universe and be unbreakable. That's not really realistic, because when you control the input and the output, you won't really send like 99999 when you're creating a path. So it helped a lot by creating strong type. F# is especially strong with that. It's very easy to create new types and make them have them some semantic meaning in the types, not just a string.
And by the way, if you are C# guy, you can use fscheck, even though it's F# library, with your C# code to generate samples for your C#.
Yeah. Which takes us to the final point, and this is the conclusion. We will start off by this obligatory F# slide.
Bragging about
this is just a propaganda slide. You can see the total lines are about half, empty lines are a lot less. Files are actually a lot less because you can fit more into a file, or it makes it easier to fit everything into a whole file. But the story is not that big of a difference when you see at the actual code lines, when you remove all the stuff.
Yeah, you see that C# code is actually, it's still something like 20-25% larger than F#. But, so when you sort of get just the meat, they're comparable, but traditionally with C#, with Java, you get a lot of ceremony, you get a lot of verbosity, which affects actually readability of the code, because you can't really see the whole thing on sort of one page. With F#, it's very efficient code, like 88% is real code, executable code. So our impression that it improved in practical aspect our work with source code, and also the fact that we have now 1/3 or maybe almost 1/4 of original number of files also helps.
Yeah. I don't think we mentioned it, but this is a comparison of the old project from 2012 and the new project. And they are not strictly like, there's no one-to-one feature set, but we've tried to extract the ones that are overlapping and compare them. But they're not, you can't, yeah, they are approximates. You they're not written in stone, these numbers. But actors are not silver bullets.
So what bad can we say about actors?
Bad can be just.
Well, you remember the benchmarks, that the absolutely fastest way to execute a piece of code is just to have direct method invocation. And when we started working with actor model, we ran some examples, including Akka bootcamp. And there were some examples of creating actors to concatenate two strings. Of course, this is kind of hello world thing, but it may give you a wrong impression that you should be creating actor for some such simple things. No, you shouldn't. You have to have some reasons for creating actors.
Yeah, because actors do add some complexity, and I think mostly to do with debugging, because an actor is asynchronous, and it's a small piece of code, and you create this large hierarchy. So it can be a bit difficult to fit it all in your head, but of course you can say that about a long stack also. But on the debugging and sort of operational side, it can be quite difficult sometimes, because this stack in every actor is so small that you can't really trace the whole flow if you're not being proactive. By doing a lot of logging, by doing, Kibana is your friend, at least for us. By doing some transactional IDs, maybe. So you start with like a unit of work ID or some kind. You create that on the boundary of your system, and that ID flows through your whole system. Makes it easier to look at logs in the whole operation of one operation. And they are not easily composable. They are sort of hard-coded. The next step in the flow is sort of hard-coded in the first actor.
So you can't easily publish a library that contains an actor to the rest of the world. Of course, if actor just consumes messages and does certain things, you can. But let's say actor is communicating with other actors. You have to do some smart things, typically dependency injection, to make it more open. But Akka Streams initiative actually tries to address this point. Yeah. But that's for another talk.
Yeah, we haven't really tested that, but we would like to. Yeah.
Yeah, we plan to test it.
So when should you use an actor or define one?
Yeah, well, as we started in the beginning, we showed this evil picture with three creatures like thread, lock, and state. And like this year, while we have been working with actor model, we really focused on our domain tasks. We didn't actually write a single instance of word thread or lock during this year, and that's probably a good personal achievement. And also actors say they're very good in single-way ordered message processing, and so if this is something that your system can accommodate, then actors are your friend.
And also the parallel computation, it's easy to, at least when you're in the sort of prototyping phase, you can experiment by splitting jobs into several smaller jobs. If you need some sort of high performance type of operation, you can split them. It's very easy to scale up. Maybe does it make sense with 10 concurrent or maybe 1,000? That's just one line of code to experiment with this, and it's very, very pleasurable to work with that sort of scalability.
And state, of course. Actors don't have getters or setters.
No, state is. It is very nice to not lock down huge collections of tasks. That's been very nice. So all in all, are we happy with our choice?
Yes, right now we're happy. We have a system in pre-production. It's actually part of it already is in production, which is showing very good scalability and performance figures. The rest of the system is under testing, but our impression so far is that we having a system which is will be much better maintainable. So in the future, probably you will need less consultants like me to work with this stuff.
Yeah.
So how are we doing this time? I think we still have more than 5 minutes.
Yeah.
So we will be around during the rest of the conference, and you can contact us on Twitter or email. But if you have some questions now, then we will try to answer. Questions? Please.
We have a mic here. Can you just get the mic as well?
Can actors have more than one subscriber? So you, for instance, like you pass the message on to the next step, which is your processing. But you might also have an actor that sends off a notification or something. So like a branching.
Yes, actors. You can subscribe to certain messages from certain actors, even though actor is sending active message to some actor. You can subscribe from different places. Also, you have broadcasting possibility with actors. Another question?
How do you handle your dependency injection with using actors?
Mm-hmm.
There's no explicit sort of framework or anything. I don't think we have sort of a, which became quite large after a while, a sort of a startup function, which basically wires up. So in a lot of cases, you start on your very main sort of function level, and you create an actor, and then you create the second actor, and you just pass it into the next one, or the actor ref.
So it's kind of sometimes it's referred to as poor man dependency injection in terms that we are not using any dependency injection framework, and we considered that we actually didn't need that. We have bootstrapper code that just spins actors and passing them other actor references or functions that retrieve code or data that is necessary to start this actor. This is how we handle. We have a few bootstrappers that we execute in the beginning of the code. And also, it's quite testable. We use test kit. Then we just pass different test actors when we test the system. So all our tests are sort of pure unit tests, in-memory tests. More questions?
One on the left or right for you?
Is that a single server application, or do you run it on a cluster of servers? Is that a distributed app or a single server app?
It's just a single server app in our case. There is something called Akka cluster, so you can, or Akka remote actually.
Well, there's Akka remote, there's also Akka cluster.
Yeah, true. Where you can deploy it to multiple servers, or say that this group of actors should be deployed to this server, but not this. But in our case, I think just the amount of computation hasn't been great enough to
yeah, performance-wise, we are fine with just single instance, but we already started the testing of Akka cluster because of failover clustering needs, because it's not good enough just to have one instance for operational reasons. And there is Akka cluster which was released about half a year ago, and which supports different scenarios. So what we're probably going to use is so-called cluster sharding, which uses persistent actors. So you have single backend, and you persist certain actors there, and so then nodes can enter and leave the cluster. We'll also be using so-called Akka cluster singleton, where you actually have just a single instance of your server, but in a clustered environment. So if it goes down, then another one will be fired up. But that's probably transition path for us, because it will require less code changes at this moment.
You started testing this last week, I think?
Yeah. We had actually, we ran some tests last week, and it requires organization where you have so-called innovation days, where people can try different things,
Hack days,
couple of days a month, and for us it was a very good opportunity to actually start using Akka cluster.
Yeah.
More questions?
So you started with one server. F# has actors as well. Do you mix the two? Do you replace everything with Akka? Is it just what's your why didn't you look at the F# kind of word?
Yeah.
Mailbox processor.
We looked at the mailbox processor because, as you say, F# has a built-in actor system, and I've actually built one smaller project using that, and it's fine. It's basically the same thing. It's an asynchronous message loop that keeps its own state and everything, but it is very limited. It is just the raw actor. There's no routing. There's no supervision. There's no, yeah. It's very limiting. So we decided to go for a bit more of a framework, because we needed some of the routing and so on.
Yeah, so like we presented like 4 main lessons, and 3 of them included things that you won't find in F# mailbox processor, which comes with persistent actors, routing, supervision, and in addition, Akka remote and Akka clustering. It's not covered by.
But it works fine. So use it for, if you have a smallish project, don't just use it. It's fine. I have it in production in a much smaller project, and I have no issues with it. So.
More questions?
I guess the time is more or less up.
Yeah. Thank you very much. Enjoy your meal and the rest of the conference.
Yes. Thank you.